Hello everyone. I hope you are enjoying the Earth Post. Today we are going to discuss about thermodynamics. Okay, don't be scared. I have tried to keep it very simple and brief. In this presentation, the discussion is primarily about the basics of chemical thermodynamics. Later on we will move on some beautiful explanation using it. As we already know, system is considered as the part of experiment separated from the surroundings either by some real walls such as a beaker, or it can be just the walls of a magma chamber separating the chamber from rest of the country rock. Another important term in this discussion will be phase, which is mechanically or physically separable part in any system with a chemically homogeneous composition. Components, on the other hand, are the minimum numbers of constituents required to describe a system. It is some chemical constituent such as ice and water are two phases of a same component H2O. I think we all know these parts, so I can skip them a little fast. The intensive variables are independent of the amount of materials present in a system. Pressure and temperature in a system do not vary depending on the amount of materials in it, do they? They don't. Volume, on the other hand, obviously depend on some amount of substance present in the system. That makes an extensive variable. Now, systems can be of three types. Isolated ones are like closed thermoflux. Neither heat nor matter can exchange with the surroundings when it is closed. Any magma body unable to transfer or receive any kinds of fluids or matters from the country rock is an example of closed system, because the magma body can radiate the heat through them. That's why we get contact aureoles around them. But if we restrict the fluid movement in them, if we imagine such a situation, then it will make a closed system. And finally, suppose if we think of some pegmatite veins, they are some examples of open systems where both matter and heat can be exchanged with the surroundings and with the system. Now, internal energy. So, internal energy is the sum of kinetic and potential energies in a system. To be very brief, in the ideal gases, intermolecular collisions are perfectly elastic ones with exactly no net loss in kinetic energy. So, the potential energy stored in them is zero, but in non-ideal gases that is not the case. However, the potential energy is stored in interatomic bondings. With increasing temperature, I repeat, with increasing temperature, increase in average kinetic energy takes place because the molecules start to move faster. It is quite natural a phenomenon. So, internal energy is proportional to the temperature. Now, the first law of thermodynamics comes from here. A very common example is compression of a gas bubble in an isolated system. Compression or expansion of a gas bubble results into turbulence in the molecules. To keep it isothermal, it has to give off or take energy from as a form of heat. A simple exchange between work done and heat to keep it isothermal. Thus, internal energy is the change in heat liberated or gained from the surroundings corresponding to the work done. So, it is, as we say, the first law for any cyclical processes, either reversible or irreversible process, work done on the surroundings is equal to the heat removed from the surroundings or vice versa. So, if we designate the total internal energy as E, then it is equal to Q plus W, where Q is the heat exchanged between the system and the surroundings and W is the work done. Now, if we differentiate it for small changes, del E equals to Q plus del of PV, and Q, if we break that, we get Q plus P del V plus V del P in normal conditions. Now, if the volume is kept constant, that is del V will be 0. So, no volume change results in no work done, because if volume is not changing, then neither system is working on surroundings nor surroundings is working on system. So, no volume change results into no work done. Thus, internal energy will totally depend on the change in heat, and the change in heat will further be measured by a calorimeter. It is possible because calorimeter is used for measuring the change in heat. Thus, the change in internal energy is equal to heat given off or absorbed during the reaction. Now, often there is a problem regarding the sign conventions. If a system is heated from outside, it will result into more kinetic energy, which will drive for more internal energy. Thus, heat gained from the surroundings will make both delta Q and delta E positive. Similarly, a tungsten filament inside a light bulb, if electricity is passed through the tungsten filament, then the light bulb hits the system and increases the internal energy, when work is done on the system by supplying electricity into it. So work done on the system is positive and so is delta E. Therefore work of expansion will therefore be negative as work is done on the surroundings by the system. Now back to the conditions. At constant pressure for work of expansion there will be minus PV, that is negative work done. So E equals to Q minus PV. If we consider it two situations, E2 and E1 and V2 and V1 for two substances. So E2 minus E1 equals to QP minus P into V2 minus V1. P is the constant pressure which we are considering. If we change the sides, simply QP will be E2 plus PV2 minus E1 plus PV1. Here comes the enthalpy term, which is the measurement of heat given off or absorbed during a reaction. So giving off energy will result into a lesser final H. Therefore H2 minus H1 will be negative or exothermic, and similarly absorbing heat will be positive or endothermic, where H2 minus H1 will be positive. And so back to the situations which we were discussing. QP will be equal to delta H, that is change in enthalpy. Now a very simple fact. Stirring some coffee powder in milk makes them both. But do they separate out if we stir the coffee cup in opposite direction? No. So what are the driving factors behind any chemical reaction to occur? It is often seen that reactions have a tendency to be exothermic. So negative delta H may be one driving factor for a reaction to occur. But there are many exceptions. The commonest one is the boiling of H2O. It is endothermic. So the other factor is randomness that drives a reaction. A real reaction takes place with an increase in randomness or entropy of the system, and that is the second law of thermodynamics. That is, when a real reaction is to occur, the entropy of the system must increase. So a positive delta S is designated as the entropy. So a positive delta S therefore will favor a reaction to occur. The combination of the two is Gibbs free energy, that is delta G equals to delta H minus T delta S. Basically the reaction is G equal to H minus Ts, where G is the Gibbs free energy, H is the enthalpy, and T is temperature, S is the entropy term. If we differentiate them, we get delta G equals to del H minus T del S. And here comes the third law of thermodynamics, which states that entropy is zero at absolute zero of temperature of a pure and perfectly crystalline substance. Now imperfection in the crystal structure or a minute change in temperature will result into some disorder or thermal motion in it. In the upcoming presentations, more will be discussed on the entropy and Gibbs free energy. So for now, let us clear one thing. Delta G equal to del H minus T del S. Okay. Therefore, if delta H is positive and delta S is negative, then delta G will be positive. Now delta H, if it is positive, then it is an endothermic reaction, which is an unfavorable situation, and delta S, as we know, if it increases then it will favor a reaction, but in here delta S is negative term, so the entropy is decreasing, so it is unfavorable. Therefore the sum delta G, that is positive, which will be unfavorable for a reaction to occur. Similarly, if delta H is negative, that is an exothermic reaction which drives the reaction, and delta S, which is positive, that is increase in entropy which further drives a reaction, will definitely drive a reaction towards delta G equals to negative, which is favorable. Therefore, the more negative delta G, the more favorable the reaction becomes towards forward direction. And if the delta G is positive, that is unfavorable but favorable in the backward reaction or reverse reaction of any reaction. Now stable state. It is the stable phase of any substance at 25 degrees Celsius and at 1 atmospheric pressure. And standard enthalpy of formation, or delta HF as it is designated later, is the change in enthalpy during the formation of 1 mole of any substance from their constituent elements. Now if we go to the elemental levels, then the standard enthalpy of formation is considered as 0 of any elements, because they are present there already, they are not formed. So delta HF of graphite, which is pure carbon, that is 0. But diamond has a delta HF of 2 kJ per mole because it is formed from pure carbon. Now Hess's law, one very interesting thing. It simplifies the calculation of standard enthalpy of formation of some compounds. As an example, in their elemental level, magnesium and silica have reacted with elemental oxygen to produce binary products MgO and SiO2 with two different delta HF values, and the two binary products MgO and SiO2 they further react to give a tertiary product Mg2SiO4 or olivine with some amount of delta HF. If we cannot simply measure the enthalpy of formation of olivine through the reaction 2Mg plus Si plus 2O2 equals to 2Mg2SiO4, then it is completely okay to simply sum up the previous three equations to get the same result as it is stated here. For the first reaction, 2 is multiplied with it because in the final reaction we have 2 Mg and the first reaction we have only Mg. So that's why we have to multiply it with 2 and then simply sum up 2 and 3, we will get the same result of enthalpy of formation for olivine. Now another important term, heat capacity. So heat capacity is the amount of heat, a simple amount of heat dq, which is involved to change the temperature by dt of a mole of a material. That is, if we consider heat capacity as capital C, then capital C equals to dq by dt. We already know the enthalpy H equals to E plus PV, and from the first law of thermodynamics we know that dE equals to dq minus PdV. So from the last reaction, that is dE equal to dq minus PdV, if we simply differentiate it with respect to dt, we will get dE by dt equals to dq by dt minus P multiplies dV by dt. Now at constant volume, dV term will be 0. So dq by dt at constant volume will be dE by dt at constant V, that is Cv. Therefore heat capacity at constant volume or Cv is the change in internal energy. Now from reaction 5, H equals to E plus PV, differentiating it we get dH equal to dE plus PdV plus VdP. Now dE plus PdV term is dq as we know. So dH will be dq plus VdP. Now if we simply differentiate it with respect to dt, then dH by dt will be equal to dq by dt plus V multiplies dP by dt. Now at constant pressure, dP term will be 0. So the heat capacity at constant pressure, that is Cp, that will be dH by dt at constant pressure or change in enthalpy. If you remember from the third slide, there also the change in enthalpy was related to constant pressure, same is here. And basically most of the reactions or experiments that are done in constant pressure condition, that is on Earth's surface. So on Earth's surface with a open condition or a closed condition, there is a uniform pressure of 1 atmosphere. So the Cp term is far more pronounced than Cv, and so is the change in enthalpy. And this change in enthalpy or the Cp term, that is easy to measure too. Now the difference between Cp and Cv is Tv alpha square by beta, where alpha is the thermal expansion coefficient and beta is the compression coefficient. These alpha and beta are two very common terms used in igneous petrology. Now further from reaction 7, we will get dH at constant pressure equals to Cp into dt at constant pressure. Now if we integrate that, we will get del H equal to Cp into integration of T1 to T2 dt. That is the change in enthalpy between T1 and T2. So the overall enthalpy at any temperature, at some temperature T, starting from a temperature of 0, that will equal to H equals to H0 plus 0 to integration 0 to T Cp multiplies dt. Now H0 is enthalpy due to potential energy of crystals at 0 Kelvin temperature along with 0 point vibrational energy, which is a kind of entropy. This 0 point vibrational energy, which is a kind of entropy and will be discussed later in some other slides. Now heat capacity increases with temperature, as you can see in the graph, that the heat capacity at very low temperature, that is low, and with increasing temperature that increases sharply, and in very high temperature that the rate of increase decreases, but still it increases. Now at very low temperature, Cp minus Cv, that tends to be nearly 0, and in solids it increases significantly at temperatures more than 1500 Kelvin. Now one very interesting part regarding the change in Gibbs free energy or enthalpy with respect to temperature or pressure, that is the GTP diagram. I am not going to discuss the steps of the equation, we will skip to the main part. So here we can see Gibbs free energy G equal to H minus Ts. Differentiating it, we get dg equal to dh minus tds minus sdt, and jumping the steps, we will get finally that dg equals to vdp minus sdt, where dg is the change in Gibbs free energy, v is the volume, t is the dp and dp are the change in pressure and temperature, v is the volume, and s is the entropy. So g is a function of temperature and pressure. Now we have two curves of G for temperature and pressure. Three-dimensionally in the GTP space, if we join the two individual G curves in temperature and pressure phases coordinates, it will appear like a sheet, like this one, the diagram at the left bottom. Similarly, if two phases are plotted in the three axes, they will intersect along a line, because if we intersect two planes, then we will get a line. So definitely they will intersect along a line. Now the projection of that line on the PT space is the stability limit of each of them. In the diagram at top right, now in GT space, below the critical temperature, alpha has a lesser G stabilizing the alpha phase. Above the critical temperature, beta is stable because the del G of beta is less. And at the critical temperature, both have the same Gibbs free energy, that is G alpha equals to G beta with a 0 del G. Now with increase or decrease in pressure or temperature stabilizing the other phase, that is beta from alpha or vice versa, that needs some change in atomic arrangements, breaking and rejoining of bonds, accompanied by a delta H value or latent heat of formation. It is the reason why some andalusite is present metastably within kyanite or sillimanite or vice versa, so which lacked the push, that is delta H. So in the lower part of the diagram, that is the G curve shows frequent change in phases, but actually they need a push as the form of delta H to initiate the change. To be more clear, the paths are not same either. So ultimately we have a 0 del G value at critical. So as we were discussing before, change in temperature for phase transitions. The change in path for alpha to beta is different from beta to alpha. Now for beta to alpha phase transition, the beta phase continues to be present in the alpha field of stability for some time when the system goes some degree of undercooling. Then it changes into alpha, an exothermic process. The reverse happens for the transition from alpha to beta accompanied by some heat supplied from the surroundings. As you can see in the diagram, the paths are labeled as dark lines and the stability fields are labeled as dotted lines. We will go to the next slide. Now this is a very popular diagram. Obviously the lines separating the phases were drawn for some experimental results. Here it is. Let's assume kyanite is getting transformed into sillimanite. Now sillimanite has a larger volume and more entropy than kyanite. Therefore both del S and del V value will be positive. So from the Clausius-Clapeyron equation, we will have dp by dt equal to del S by del V, that equals to positive. So dp by dp will be positive. So we will get a positive gradient separating the two phases. Try for the other phases as well. It is very interesting. You just need to know the volume and entropy of each of the phases. Now, the final topic for today is reaction curves. Now solid-solid reactions are generally expressed by straight lines in the PT graph, because the del V and del S both are limited with increasing pressure or temperature, keeping the slope more or less same, resulting into a straight line. In case of devolatilization reactions which involves fluids, so the increasing temperature, volume increases significantly, but as pressure accompanies the reaction soon, so the volume gets shrinked and the main change is driven by increasing entropy. Now we know that entropy increases with temperature too. So the magnitude of the positive value of dp by dt increases with increasing temperature or increasing pressure. So with a change from gentler to a steeper slope, resulting into finally a curved line, not a straight line. So we will end here today. On the next presentation, we will discuss more about Gibbs free energy.